Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. Before we go, let me introduce myself. My name is Ramanuzha Gunawan. I'm an engineering student, major in mechanical from Diponegoro University. Today, I want to present my research. It's about simulation of thermal dispersion in location of development of diesel power plant using computational fluid dynamic methods. So here it is. Before we go further, I'm bringing you some outline for this presentation. There are preface, method, result of the research, and the conclusion. For the preface, in the North Maluku region near the Halmahera waters, it is planned to build the diesel power plant or PLTD to fulfill the electricity need in the area. PLTD activities itself produce a waste of heat water from the rest of PLTD cooling system processes. The hot water causes the pollution in the form of the heat in the water. In the study, numerical simulation was conducted to determine the thermal dissipation pattern of the PLTD hot water and find the optimal placement of the inlet air cold of the PLTD. So, there is Halmahera waters, where it's located in the North Maluku in Indonesia. This picture is bathymetric maps. Bathymetric maps is a map that describes the shape of the seafloor configuration that expressed by depth figures and depth line. Simulation and analysis of distribution pattern of wastewater temperature of PLTD cooling water in the Halmahera waters were carried out using 3D Computational Dynamic or CFD. Modeling input is using temperature data, bathymetry, and the ocean current. The modeling is done to predict the extent of the effect of the thermal pollution by PLTD cooling waters. So, we can determine the optimal placement of the intake and the discharge outlet to avoid rising natural temperature above the permitted standard. The UDF feature in this research is make user more freedom to develop boundary condition, material properties, and change modeling parameters to improve post-processing. Where in the modeling of this thermal dispersion, the function of UDF is used to arrange the boundary condition at each depth where the current speed has a different value. Now is the validation. Validation is done to determine the boundary condition that will be used in the modeling. Validation simulation were carried out based on the previous research on thermal dispersion carried out by Sheikh Muhammad Asfaq in 2015. The geometry of the journal is a 3D model with dimension, with length is 70, width is 50, height is 8, and diameter of the head outlet air is 2.5. Now, after the simulation, the counter result of the temperature distribution between the journal and the simulation have a match, where the error value is below 10%. The error value is shown in the table. There is a local temperature with an error is 0.53% and the maximum temperature is 6.13%. And there is a geometry design that used in this research. We can see there is a diameter discharge outlet and width, right left border, left right border, and the shoreline. And there is an explanation about skewness that used in this research. There are some value like minimum skewness, maximum skewness, and average skewness. And there it is, the boundary condition that used in thermal dispersion modeling simulation based on the result of the journal validation that been carried out. Parameters for modeling boundary condition are presented in table 2. Now, there is the result of the research. In the study, we modeled two variations of the ocean current. There are a constant current and the UDF current. Furthermore, the temperature distribution of each depth and each distance of the discharge outlet position is observed. From the figure, We know that temperature contour at depth of 5 meters, where the discharge outlet position is. The maximum temperature rise for the constant current model reached 37.14 degrees Celsius, and the for UDF current model it reached 37.13 degrees Celsius. From the simulation result at the depth of 1 meter has a temperature value is 31.35 degrees Celsius. In the area depth below 5 meters, the value temperature rise is lower. This happens because the lower part of the water with high temperature has a lighter density, so that the water moves upward, causing the upper water rise in the temperature. And there is a temperature chart against the distance of north from the discharge outlet for each depth. From that figure, we can see the graph of the constant current. The lowest temperature is 30.8 degrees Celsius at the depth of 7 meters. From that figure, we can see the temperature chart against the distance of north from the discharge outlet for each depth. We can see for constant current, the lowest temperature is 30.8 degrees Celsius at a depth 7 meters with a distance of 210 meters to the north from the position of the discharge outlet. Whereas for UDF current, the lowest temperature is 30.6 degrees Celsius at the depth of 4 meters with a distance of 210.22 meters to the north from the discharge outlet position. The temperature distribution value of the UDF current model has a better result compared to the constant current model. This is because the UDF modeling of the ocean current being modeled are closer to the actual condition, where the seawater velocity will be smaller with increasing depth. There is a figure that shows a graph of temperature distribution of the distance from the seashore. And the next is the conclusion. The first is the thermal distribution pattern of the cooling water of PLTD is affected by the flow pattern or sea currents, where the sea currents here are modeled with the north direction, causing the heat distribution to point north from the discharge outlet position. The second is the highest temperature due to thermal dispersion for constant current is modeling at the depth of 5 meters, which is 37.15 degrees Celsius, and the lowest temperature value is 30.8 degrees Celsius at the depth of 7 meters. For the modeling ocean current using UDF, the highest temperature rise value at the depth of 5 meters, which is equal to 37.13 degrees Celsius, and the lowest temperature value is 30.61 degrees Celsius at the depth of 4 meters. The next is the value of the lowest temperature rise due to thermal dispersion is in the area of distance of 210 meters north from discharge outlet. For the constant current model is 0.63 degrees Celsius, and the UDF current model is 0.552 degrees Celsius. And the last one is the optimal placement for cooling water. Index of the PLTD is at a depth of 7 meters for constant current model, and the depth of 4 meters for UDF current model, with a position as far as 80 meters from the beach with a distance 210 meters from the discharge outlet position. I think it's enough for my presentation, and I'm say thank you for all of you. Thank you.